Welcome back. In the last lesson, we covered cross-entropy, an error function that can be used to calculate the total error associated with our linear model. The more incorrect our model is in separating our data, the larger its cross-entropy value, and thus the larger the error. What we'll do now is take this random line, which we plotted earlier, and calculate the error in its classifications. How well does this line separate our data? We'll start by defining a function right over here. Def calculate error, which takes in our line parameters, and now the second argument will pass in all of our points, and the third argument corresponds to the labels. We'll call it y, which I'm going to explain momentarily. And let's call our function down below calculate error. We'll pass in the line parameters, which we'll just copy and paste. And now the second argument, pass in your points, which I believe is called all points. Indeed it is. And now the third argument is going to denote the labels. Since we're classifying points in two discrete classes, either top or bottom, the points in the top region will give a label of 0, and the points in the bottom region will give them a label of 1. The simple reason being, as we saw earlier, given our linear parameters, any point on top had a negative score, and any point on the bottom a positive score. So, instead of 100 points, let's put this back to 10 for now. And what we'll do is actually print the vertically stacked array. Clearly this array has 20 rows. The first 10 rows correspond to the points in the top region, and the last 10 rows correspond to the points in the bottom. We'll need to make an array of labels with 20 rows. The first 10 rows will be all zeros, so as to denote that we're labeling all points in the top region as 0, and the last 10 rows will be all ones. So back to our code, we'll set a variable y is equal to numpy.array. First, we'll have our zeros, numpy.zeros, number of points, and then our ones, numpy.ones, number of points. So we'll have 10 zeros corresponding to every point in the top region, and 10 ones for every point in the bottom, 20 labels in total. If we print this, print y, instead of it being a single row and 20 columns, we need to reshape it into having 20 rows in one column. This is necessary, that way when we apply the cross-entropy function, the dimensions are compatible when performing matrix multiplication. So we'll write .reshape, and we will reshape it as number of points times 2, such that our array will have 20 rows, and we want them going along a single column. Printing this, much better. This is exactly the result that we need. Recall that this was our cross-entropy equation. Clearly, to write this equation, we first need to determine the probability of every point being positive, which we've already done over here. So we'll just copy and paste it right onto our function, and we'll call this p instead for simplicity. And you can delete what we have here, and we'll simply copy and paste that. This is named points, not all points, and delete that as well. Nothing new so far, we just got the probability of every point being positive. And as the equation suggests, we have to take the logarithm of all probabilities with np.log p and multiply it by the label. What we'll do actually is take the transpose of the first term before multiplying it by y. Transpose times y. By taking the transpose of the log of the sigmoid, this becomes a matrix of a 1 row by 20 columns, and by performing matrix multiplication between the two, we get a 1 by 1 matrix. If you're not sure why, make sure to revisit the matrix multiplication tutorial in the crash course. But notice how the points in the top region have no effect on the final value of our first term. This does exactly what we needed to do. It takes the log of the probabilities of all the points in the blue region, adds them up, and cancels out anything from the top region. Let's go ahead and put in the second term, 1 minus p. This takes the probability of every point being negative, in this case of a point being red. We'll take the natural logarithm, np.log. Once again, take the transpose, but this time multiply it by 1 minus y. 1 minus the label, this time to cancel out any points from the bottom region. Adding these two up gives us our total cross entropy. But don't forget, by convention, when computing the error function, we consider the average, not just the sum, which is why we divide by the total number of points m. So we will just wrap this up in brackets and multiply everything by 1 over m. The total number of points is simply the number of rows inside of the points array, which we can obtain by setting m is equal to points dot shape, which, as you know, well, this should be brackets, which, as you know, returns a tuple of our array's dimensions. The number of rows is at index 0. And don't forget to take the negative, since logs of probabilities ultimately result in a negative value, and we're done. That is our cross entropy equation. Let's just set it equal to a cross entropy variable and simply return our value. Return cross entropy. In our last cell, make sure to pass in all of the correct arguments, and we will print the return value of this function. We get an error. Tuple object is not callable. Seems that there's a mistake somewhere here, and I forgot to add a multiplication symbol. Let's try this again. And we get an error of 0.3178. Our linear model, how well does it classify our data? Well, it does it with an error of 0.317. What if we tried a line that classifies almost everything completely incorrectly? Let's declare a line. We'll choose a line with a y-intercept of 0, a weight of negative 0.1, and W2 of negative 0.15. Let's run every cell. Clearly this line misclassifies all the blue points. It classifies them all in the negative region. As such, clearly this line has a much bigger error than the previous one, 0.84. This is a very bad model in classifying our data. Alright, that is all for using cross entropy to determine the total error of a linear model. The next step is to use gradient descent to minimize the error and come up with the perfect line. Let's do that in the next video.